Hi there guys, as promised today I'm going to go over the code for the Arduino in my homemade Arduino controller with Unity game. First we're going to take a look at the controller, basic hardware setup, and then we're going to run through the code so we can see it in action. First of all, let's take a look at the hardware. As you can see, first of all, we have a Arduino Uno. It's hooked up. I'm using 5 pins, unlike the introduction video. I used a couple more, but I made some adjustments. So I'm using 4 pins for the buttons, 1 for the LED, and I have power from the Arduino as well. All of this could of course be replaced with maybe a AT-tiny 45. I don't think you can do it with an 85 because we need to establish that serial connection to your PC, and that requires connection ports, MOSI ports. And if you're going to use the 85, you're going to use all the ports just for the buttons. So let's take a look at the protoboard. And you may notice something has changed. Well, I have my LED, it's lighting up as red, and you can't see, but on my screen I can make it switch. There we go. It's now green, meaning it should be active, red, inactive. We have the 4 buttons, and right now I'm having I'm using a AT-tiny 85 right there, and that's just a replacement for some MOSFETs, because alternately I had to use quite a few of these to create a OR gate on OR gate, because I want to send one signal through one wire, and I needed to turn these on or off depending if there was this wire was high or not. So when the wire is high, the green one is on. When the wire is low, the red one is on. So the easiest thing was to simply, instead of setting up a network of MOSFETs and creating my logic gate, I programmed my logic gate onto the AT-tiny and just hooked that up instead. And that is also what you often see when you buy professional hardware, that most logic gates have been replaced with either Atmel chips or some sort of designed integrated circuits where they have the logic gates replaced with chips. In front of the buttons, each button is wired up, so I have a wire that goes into the left side of the button. That's the power, so it's 5 volts in. On the right side of the button going out, I have a cable that's running over to the Arduino, and after the cable I have a pull down resistor. So I'm going to remove the white one. So there you can see, yellow one is power for this button, and then this yellow wire out. So if I remove the orange, you should be able to see. And then in this case I'm just using 1K resistors for each button. For my LEDs I'm using 220 resistors as usual, and nothing on the AT-tiny. So that's the hardware. That's the easy part. And now let's take a look at the software, the hard part, if you want, or the more interesting part for some. Well, let's get rid of that extra webcam down there. There we go. First of all, I'd like to show you the program for my AT-tiny. Let's fire up MonoDevelop so you can see the code. It's very small on screen, so in MonoDevelop we can just open a new file, I'm hoping. a empty class, yes please, and we're just going to call it test. Yeah, that's a bit off screen, sorry about that. So I'm just going to copy this. Let's make sure we bring everything. There we go, paste, and we can now zoom. Oh, that is the logic gate, my AT-tiny replacement. What I have defined is that's input on pin number 2. And if you remember, the AT-tiny is configured like this. So pin 0, 1, 2, and it's only those 3 I'm going to use. And there you can see if I needed to connect make a serial connection to my PC, I would be using pin 1 and 0. So yeah. Anyway, we're using these 3, 0, 1, and 2. And we have them right here, just in a different order. We have 2, 0, and 1. I, O, and P. First thing I do is to define input mode for the wire from the Arduino, output modes to the 2 LEDs. I simply check or I read the wire. If the wire is high, then I'm going to switch the LED on and the other one off. If the wire is low, then it's the opposite. That's basically it. That's your basic OR gate. So let's get back to the Arduino. We can minimize this one, and then we're going to take this one and copy everything so you can see what's going on. Let's get rid of that window right there. There we go. Up to the top. So instead of using ints like I often do, in this case I've defined button A, B, C, and D. Or in the Unity game they are actually named 1, 2, 3, and 4. You can say I'm inspired by many modern consoles where they are naming the buttons by letters instead of numbers. And these are the pins. On the Arduino, the buttons are directly hooked up to. I also have my LED pin, which is indicating whether there is a connection to the Arduino or not. And we are defining a incoming byte. And the reason for that is because we're going to get some data from Unity. Of course we're going to send data, but that means nothing. We don't need to prepare sending data like that. We only need to prepare to receive data, and that is what this is for. And that is because the indicator on my board needs to light green when it's hooked up to the game. So when I start the game, it needs to check is the Arduino available, and if it is, then it's going to send the signal I'm ready to play. And the Arduino is going to translate that signal into turning the LED on. I have this one called a boolean. That's just a flip switch, and it's connected. That's it. That's it. Whoa, that that is hard to say. That is its name. Yeah, let's try that. And it's set to false by default because, as the name states, it is not connected when you turn it on. I define my input and outputs right here and instantly switch the LED to low, meaning it's off. I start a serial connection at 9600 baud. I may change that in the future. And here we have our main loop. Let's skip that and we'll get back to that in a second. I have this function called handshake. It's not really a handshake. If you know how they work, this is not it. This is just an indicator for my LED to work. So whenever I call this function handshake, it's going to flip this boolean called isConnected, meaning it's by default it's false. It's going to switch it to on or high or true if you want, and then it's going to turn the LED to high. Else it's going to turn the LED to low. So that's how I switch the LED back and on and off, sorry. And that's really just sending a signal to the other chip, the AT-tiny, to turn the LED on or off. Yeah, that's now you're connecting through 2 chips, but that's one way to do it, and I think it's the most easy way to do it. Last thing we have is this function called button off. And that's instead of writing a long debounce function, because when you press one of these buttons, you'll get a signal that lasts maybe half a second, even though you just click it once. That half second, the computer is going to receive multiple clicks, so as if you were clicking it very, very, very fast. And I try to stop that by turning all the buttons off as soon as possible. So I made this function called button off, or I try to make them low. And we'll see that up in the main loop. So here we have main loop starts, and the first thing I do is actually turn the button off to make sure every time we start this loop, the buttons should be low. This could also introduce another problem. If a player holds the button down, it will actually turn it low, then register high, so you will have this flickering value if the player holds the button. That's something to take into consideration when you are developing your game. As for the hardware part, this is fine. So we get sort of this rapid fire function built into the button. Next thing we do is simply just read each button, A, B, C, and D. And we're just checking if they're high. And you can see that's a bit silly, because you could write a case switch or a for function to test each button. But since I'm just going to forward each button, I have actually wrote a if statement for each button. So if read A is high, send the number 1 to the line, and then wait 10 milliseconds. 10 milliseconds is hardly anything, but that delay also helps us to decrease the debounce of the buttons. However, the delay may also feel as a delay for the player. 10 milliseconds they should not be able to feel, but if you add it maybe 50 or something, you'll feel a lag. And then people will complain that the thing is unresponsive, or there's all sorts of problems, but that's all caused by this delay. You could even remove it, but that may just introduce or reintroduce the debounce, bouncing of the buttons. So either way, moving on, after reading all 4 buttons, then we're going to check the serial connection for input from the computer. So if the computer is sending data, that's what this says. If not, then it's just going to skip the entire thing. If the computer is sending data, then we're going to look for the letter E, O, not 0, that's an O. And when we find the letter O, we're going to read the very first number after the letter O. And if that number is a 1, then we're going to do the handshake. Once that is all done, we're going down, cleaning out the rest of the bytes in case there is more text or anything on the serial connection. It's just going to check. That's basically it. That's the code. That's the Arduino code, and it's not that big actually. So we got a game controller, a basic game controller on less than 100 lines, including spaces. For the hardware part at least. Now, the next video, I'm going to show you the coding of Unity and the code used in Unity. I'll post a link in the description with the code for my Arduino and my code for the MV-teknik. Thanks for watching, comment, rate, subscribe, and I'll see you next time.